All right, what's up, guys? Mr. Rushka here. I've just set a timer for 45 minutes, and I'm just going to try to go as far as I can in 45 minutes. These are actually really short sections, so I'm actually hoping to get through first derivatives in this lecture, okay? And then we can just spend a couple days just working on this and ironing it out in class, okay? That's kind of my plan right now, all right? Sounds good. Okay, these are huge topics, okay? So if you remember in pre-cal, okay, in pre-calculus, my pre-cal kids just had this on their test. There were some test problems where you had to find the maximum and minimum values of a function over a given interval, okay? So, it'd be like, hey, there's a rectangle and its area is 200. Find the length and width that maximize the perimeter of the rectangle, okay? And you'd have to create a function and then find the maximum, plug the perimeter formula into your graphing calculator, graph that function, okay? And then you'd have to find the value of W or the value of L that maximizes the perimeter, okay? So the only way for you to do that was with your calculator, okay? In pre-cal, you don't learn to, by hand, ever, learn how to find the maximum value of a function. In calculus, you learn how to find the maximum and minimum values of a function over a given interval, okay? So we call these extrema. Extrema are minimums and maximums, okay? Minima is the correct plural form. Minima and maxima, okay? Both local, right? Both local and absolute. Okay, so a local minimum, right, would be any sort of valley. Any trough or valley you see in a function. Right? Same thing for a local maximum. A local maximum is any peak or hill you see on a graph, okay? All right, the absolute minimum is the lowest local minimum. Well, it's either that, it's the lowest value overall, the lowest overall value. The lowest overall value of a function. And it's either going to be the lowest local minimum, or it's going to be one of the endpoints. We'll see that later. Absolute maximum. Okay. And absolute maximum is the highest overall. It's the highest peak. So think of a mountain range, right? Right, there are many mountains, right, in a mountain range. And every mountain has a peak, has a local peak, right? But only one of those mountains is going to be the highest peak, okay? So Mount Everest, right? There's lots of tall peaks around Mount Everest, right? But only Mount Everest is the highest peak in the Himalayan mountains, okay? All right, so, yeah. Or I do want to say a function does not have to have a maximum or a minimum on an interval, okay? Yeah, so look at these functions here, right? This is a good example, actually, right? So here we have a graph, okay? The minimum here, right? There's one trough here. there's one minimum right here that's both the local and the absolute. It's a local minimum because it's a trough, right? It's the bottom of a valley, a little valley on our graph here. And it's the absolute minimum because it is the overall lowest value, okay? And then the maximum here, right? Here, this is a good example. The maximum here, right? It's not part of, like, it's not a peak. It's not part of, like, but it's an endpoint, okay? Sometimes, okay, the highest or the lowest or both, the highest or lowest values of a function over an interval will just be at the endpoints of that interval. So right here, the interval from -1 to 2, okay? The maximum value of f on that interval is right here, okay? Good stuff, okay? Here, this is a good one. This function, right, it has a minimum here, right? This is a local minimum and an absolute, right? It's a local minimum because it's a trough, and it's an absolute minimum because there's no values here that are lower, is the lowest possible. There's no maximum here, right? Because here where the maximum would be right there if there were one. But because there's a hole in the function there, there's actually no maximum. What happens is if you guys were to give me a value like, hey, wouldn't they our absolute maximum just be really close to that? Well, no, because I could give you a value between that open endpoint there and then that red dot that you drew, and I could say, no, this one's higher, okay? Same here, right? There's a maximum up here. There's actually no minimum. There's no minimum, right? If there were a minimum, it'd be right here, okay? And you might think, okay, well, the minimum's not here, right? Maybe, wouldn't it just be the 2 points right next to it? Well, again, we're talking about real numbers here, guys. However close, I'm trying to think of the best way to explain this. You might pick a point to the right or left of this hole here and tell me that is the, quote, new minimum. But the way real numbers work, I could just give you an even closer number, right? I could give you a number between the point you gave me and the hole and say, no, this one's even lower, right? And that process can go on, and so on, okay? All right. So here we go. This is a pink sheet right here. Extreme value theorem, okay? If f is continuous on a closed interval, then f has both a maximum, and this is absolute maximum, both an absolute, that's probably important to add actually, maximum and an absolute minimum on the interval, okay? Good stuff. How do we find them? Okay? Well, our relative extrema, there's 3 types, okay? So we're either going to get relative maxima, I'm going to say local. So you can find your local maxima, your local minima, and what's called inflection points. Right, inflection points, okay? You can find what's going to be true, okay? So if you have a function, right, that's defined, that's continuous on an interval, on a closed, if you have a function f that's continuous on a closed interval, then all of its local maxima, all of its local minima, and all of its inflection points on that interval will have the property that f prime of x at these points equals 0, or either equals 0 or is undefined. Either equals 0 doesn't exist. Okay? Either equals 0 or it doesn't exist, okay? And these are all in one category. They're called critical points. That's actually the definition. Okay? So maybe pink sheet this if you want, but it's so important, basically. It's basically so important that this is a definition you should kind of just know. Okay? It's like learning the Hail Mary, the Our Father. You should probably just like know it, okay? So if they ask you on the AP test to find the critical numbers of a function, you take its first derivative, you set it equal to 0, or you see where the first derivative doesn't exist, okay? If at any point it equals 0 doesn't exist, then that point is a critical number, okay? Good. Okay. Definition of relative extrema. Yay! Yep, so here it is. Okay. So here we go. Here's a function. Here's the graph of a function. Okay. It's continuous on this interval here. Okay. And notice at this point, at that point, the derivative does not exist at that point. It's a cusp, okay? So this is a critical point, okay? And every critical point is either going to be a local maximum, a local minimum, or an inflection point. Here, it's a local maximum, okay? It's a mountain peak, okay? This point here is higher than all the other points on this graph in this location, in this interval, okay? Same thing over here, okay? F prime of C equals 0, okay? So this is a critical point, okay? And again, every critical point is either going to be a local maximum, a local minimum, or an inflection point. This one is a local maximum, okay? All right? Cool. Here we go. Relative extrema occur only at critical numbers. There you go. Notice it says relative, okay? Don't get this mixed up, okay? This says not absolute. Absolute extrema can happen at the endpoints of an interval, which are not always critical numbers, okay? So over here, right? Yeah. So there you go. Cool. Right, this is relative extrema. What's the difference? Okay, relative extrema means the point is either greater than or less than all the points that are really close to it. Absolute minimum, an absolute minimum is lower than all the points on the entire interval. An absolute maximum is higher than all the other points on the interval, okay? All right, hopefully some examples will help, okay? Cool. Let's do example 1. F is continuous on a closed interval, a comma b. That's what this expression means. It's differentiable on the open interval, a to b. Okay. Which of the following could be false? Okay. This 1a right here. This is what? Look at your pink sheet. This is just the mean value theorem. So yeah, this is definitely true. Because the theorem is true. It can literally be proven true, okay? Here you go. F prime of C equals 0 for some C such that A is less than C, which is less than B. That's not true, actually. And I can draw a counterexample right now. Let me draw some coordinate axes, okay? Let's just draw this line here, okay? And there, let's mark off an interval, let's say from A to B, all right? Sorry. Here's a function. Here's a function. Here's an interval. Here's a function. Here's an interval. Okay, right here. Notice this function is continuous and differentiable on the interval, but there's no point here where the derivative or the tangent line, the slope of the tangent line, equals 0, okay? There's no point on here, okay? So this is not necessarily true. So yeah, not necessarily true means what? It could be false, okay? And we just saw a counterexample, okay? F will have a minimum value on that interval, whether it be like a hill or maybe one of the endpoints is the minimum value. All right, same thing with D, C, and D, okay? Oh, excuse me. All right, example 2. Example 2, function f is defined in this closed interval and satisfies, all right, f of 0 equals f of 1/2 equals f of 1, okay? So the points 0, comma, y, 1/2, comma, y, and 1, comma, y, they all have the same y value. Draw a horizontal line that passes through all 3 of these points. All right, on the open interval 0 to 1, f is continuous and strictly increasing. Which of the following statements is true? Okay. Part A, f attains both a minimum value and a maximum value on the closed interval 0, 1. That answer kind of this. So I'm looking at this first one here, guys. I'm checking out this first one. Okay. Let's think about this. Okay. So f is defined on the closed interval 0, 1. Okay, and it's continuous on the open interval, strictly increasing. Okay. So let's think about this. I'm looking through my notes. Okay. Here we go. This says if f is continuous on a closed interval, then f has both a maximum and an absolute value, minimum on the interval, okay? The problem just says it's defined. It just says it's defined on the closed interval, okay? So I don't think I don't think this first one has to be true. All right. Or maybe it is. F is continuous and strictly increasing. It says defined. The function is defined on the closed interval, okay? Let me check my answer. Unfortunately, I'm doing this at home. I left the notes answer key at school. Let's just look at it on Schoology. Here we go. Okay. All right, cool. So the answer is D. And here's what I think is going on. What I think is going on here is... Okay, what I think is going on here, so the answer is D. The function contains neither a minimum value nor a maximum value on the closed interval. What's going on here is like, let me draw some coordinate axes, okay? So imagine we have our interval, okay, A to B, or 0 to 1. What I think is going on here, so we know that 0, 1/2, and 1 all have the same y value. It's defined on the closed interval. Okay, on the open interval, f is continuous and strictly increasing. So here, strictly increasing, sorry. Here's what's going on, guys. Here's what's going on. I see what's going on. Oh, crap, sorry. Here we go. This is what this graph looks like. So I'm just gonna make this bigger. There we go. So here's what's going on. So on the open interval, so between 0 and 1, not at 0 and 1, but between 0 and 1, this function is continuous, okay? All right, but it's not continuous at the endpoints. The theorem says this theorem, the extreme value theorem, says that f has to be continuous on the closed interval. Here, it's only continuous on the open interval. So the extreme value theorem doesn't apply. It does not satisfy all the conditions you need to apply it, okay? All right, so boo-hoo, it's unfortunate, whatever, okay? Then what's going on here is there's neither an absolute minimum nor an absolute maximum on this closed interval, okay? And that's because at these endpoints here, right, you can tell me, oh, Mr. Rushka, like, can't you just say the new minimum is right here? Well, no, because if I zoom in, the way real numbers work is I can find you a value halfway between this point you gave me and the endpoint, okay? And I can say, no, this one's lower. And you can say, okay, what about this one? No. So that's just the way real numbers work, okay? Same up here, right? You might say, Mr. Rushka, isn't the new maximum just right here, right next to that endpoint? And I would say no, because there's like, basically with real numbers, because real numbers are a continuous quantity, there's no such thing as a number that's right next to that endpoint, because you can always just chop everything in half when you're working with real numbers, okay? I don't know how else to explain that, right? I guess you can say like, hey, Mr. Rushka, I just drew the shortest segment possible. And I said, no, I can draw a shorter one. You can say, no, I can draw an even shorter one, right? That's how it is with real numbers, okay? There's no such thing. A lot of the time, there's no such thing as like the smallest possible distance, okay? Yeah, let me stop talking before I confuse you. All right, example 3. Let g be a function given by g of x equals x squared e to the kx, where k is a constant. For what value of k does g have a critical point at x equals 3/2? So this is really getting into the meat, okay? There are going to be tons of problems like this, guys. Like, you are not going to stop seeing these. So they give us a function g. K is just some constant, okay? For what value of k does g have a critical point at x equals 3/2? What does it mean? So let's think about this, guys. What does it mean for g to have a critical point at x equals 3/2? All right, I feel like if I asked you guys this during lecture, you'd all just give me blank stares, and I would either, capitulate to your blank stares and just tell you the answer. All right, but the right thing to do would be like, hey, no, just go look in your notes, okay? Look in your notes, okay? What's the definition for a critical number? Either f prime of c equals 0 or f is not differentiable. So f prime or, so this is or f prime of c does not exist. Okay, those are the two options, okay? So for our function down here, g of x, to have a critical point at x equals 3/2, that means g prime of 3/2 equals 0, or g prime of 3/2 doesn't exist. Okay, so let's do this, okay? So here we have g right here. Let's find g prime of x. G prime of x, this is a product rule, okay? So it's going to be u prime v plus u, then v prime, and that'll be a chain rule. I got to multiply by k. Okay, so g prime of x is this. Boom. Okay. What do we want to do? So we want to have g prime of 3/2, which is going to be just plug in 3/2 wherever there's an x. So 2 times 3/2 times e to the 3/2 k plus k times 3/2 squared times e to the 3/2 k. Okay. What we want is we want for this to basically equal 0 or be or undefined. Okay. Since we're not working with a rational function here, our best bet is it equals 0. Okay. So let's simplify this. This first term becomes 3e to the 3/2 k. The second term becomes 9/4 e to the 3 halves k. Right, we want that to equal 0. So we got to start solving for k here, okay? So let's, I'm going to subtract 3 e to the 3 halves k from both sides. I'm solving for k, okay? Okay, so that cancels. We get 9/4 e to the 3 halves k equals negative 3 e to the 3 halves k. All right. All right, so then, oh, you know what I'm going to do? Actually, that was a bad idea. You know what we should just do? We should just, so we'll start this, we should just factor out e to the 3 halves k. I'm sorry. Makes it a lot easier if we just do that. Okay. So we need, basically, that means we need e to the 3 halves k to equal 0, which isn't possible. Okay, I'm stuck. Let's look at the answer key. Yeah, it says no solutions. Oh, sorry. So I forgot something. I forgot this k here when I copied down to this line. So there should be a k here. So it should be 3 plus 9/4 k. So this should be, this either, okay, so let's recall. Okay, so let's factor out. So I'm sorry, guys. I forgot what I did was I forgot to copy this k down to here. So I forgot to move this k down here. Sorry about that. Okay, then now I have solutions. So I factor out an e to the 3 halves k. I get this. Okay. So remember from algebra, the way you solve this kind of an equation is you set each individual factor equal to 0, okay? So if you set this equal to 0, there's no solutions. So you can't do that. So we set this equal to 0, we get 3 plus 9/4 k equals 0, or 9/4 k equals negative 3, or k equals negative 3 times 4 over 9. Which equals negative 4/3, okay? So there's our answer, okay? So what this means is, okay, look at this function here. When k equals negative 4/3, then g prime of 3 halves equals 0, and g has a critical point at x equals 3 halves. Okay. Let's move on. Determining intervals on which a function is increasing or decreasing, okay? So this was all about trying to find where a function has a critical point. So where a function has a minimum, either a local minimum or a local maximum, or where it has an absolute minimum or an absolute maximum, okay? That's what this was all about, okay? Okay. This next part is about determining where a function is increasing or decreasing, okay? So critical points, this 5.2 is all about analyzing points of f, points of a function. This is going to be more about intervals. There's going to be intervals on which a function is increasing or decreasing, okay? So you learned about this in pre-calculus, but you were taught to look at a graph and tell off of a graph where a function was increasing or decreasing. Now, we're going to learn how to do it by taking a first derivative, okay? So here are the definitions of increasing and decreasing, okay? These are very mathematical, very rigorous. Hold off on this for your pink sheet for now, okay? I like the test better. These two things, I would say these are pink sheet material. These are much better. So this is actually pretty easy. This is a pretty easy concept, okay? Right? So this is literally just saying you take the first derivative. If f prime of x is greater than 0, then increasing. If f prime of x is less than 0, then we're decreasing. Okay? So let's look at this first example. Okay. Right here, okay? So what are they asking us? Find the critical values of f of x. Okay, that's the pink. Okay. What else do they say? They say state the intervals over which f of x is increasing and decreasing, okay? So, one thing kids get really confused about, you need to make sure you remind yourself, we are looking at the graph of f prime. This is not the graph of f, okay? This is not the graph of the original function, and we don't need the graph of the original function. Screw that graph. I hate that graph. No, I'm kidding. I'm sure it's great, okay? This is the graph of f prime of x. You need to make sure you remind yourself of that absolutely constantly, okay? Absolutely constantly. Okay, so let's do the pink part. What are all the critical values of f? Look at your notes, guys. Look at your notes. What is the definition of a critical value? That means, definition, f prime of x equals 0 or doesn't exist, okay? All right, we have a graph of f prime. We can tell off this graph where f prime equals 0. It's going to be wherever it has x-intercepts, okay? So the critical points of f, right, are going to be 0, 2, and 4. You see that? 0, 2, and 4, okay? So critical points, so crit points at x equals 0, x equals 2, x equals 4. Boom. Done. Done with the pink part. Orange. State the intervals over which f of x is increasing and decreasing. So for increasing, right, that's wherever f prime of x is greater than 0. So we look at the graph here. F prime of x, this is the graph of f prime of x. So f prime of x is greater than 0 wherever our graph is above the horizontal axis, okay? So that's going to be, so for increasing, that's going to be 0 to 2, open and exclusive, so 0, 2 with parentheses, right? It's not increasing at 0 or at 2 because it's equal to 0 there. And then 4 to infinity, Decreasing, it's going to be decreasing. It's going to be decreasing, right, wherever f prime of x is less than 0. So here's the graph of f prime. So wherever this graph is below the horizontal axis is where I'm decreasing. So 0 to negative, so negative infinity, 0. I guess I should probably use a union symbol. Union, and then 2 to 4, right? It's below the x-axis from 2 to 4. There you go, yay! And that problem's done, okay? Intervals on which f is increasing or decreasing, okay? Find the intervals on which f of x equals x cubed minus 3 halves x squared is increasing or decreasing. Again, look at your your notes, okay? F prime of x is greater than 0. That's going to be where f is increasing. For decreasing, I'll use a different color. It's going to be where f prime of x is less than 0. Okay, so what we do is we take this first derivative, okay, and then it'd be what, minus 3x, right? Yeah. All right, and then we're going to graph this guy, okay? We can make a sign chart, we can graph it, whatever you want to do, okay? So, let's factor out 3x. Okay. Let's make a little sign chart then for f. So this is f of x, right? To make a sign chart, again, you plot all the zeros in vertical asymptotes. There's no vertical asymptotes for this function. There's just zeros at x equals 0 and x equals 1, okay? So we plug in a function. If we plug in a value to the left of here, let's say -1, we plug -1 into here, we get, it's going to be positive, right? It's going to be positive, I think. Yeah. So it's positive here. There's another 0 here. So let's test like, I don't know, let's test like 1/2. If we plug 1/2 into this, we get 3 times 1/2 times 1/2 minus 1, which is 3/2 times 1/2, which is 3/4. Okay, so that's going to be positive as well, right? Right? Did I do that wrong? I feel like I did something wrong. Yeah, that's going to be negative. What am I doing? That's 3/2 times -1/2. I'm sorry, guys. It's negative. So it's going to be negative here. There we go. I make mistakes. It's okay to make mistakes. And then over here, let's test 2. 2, it's definitely going to be positive again. Okay. Good. So here's the graph of, sorry, this I should say f prime. This is the graph. This is a sign chart for f prime of x, okay? So wherever f prime of x is positive, so negative infinity to 0, union 1 to infinity. On that interval, it's going to be increasing. I should say f is increasing. Okay, and then where f prime of x is less than 0, where it's negative, so 0 to 1, f is decreasing. Okay, there you go. All right. The guidelines for finding intervals in which a function is increasing or decreasing, okay? Yeah, so basically what we did, okay? So we basically made a sign chart for the first derivative, right? And then notice when doing so, we actually found the critical numbers as well, because where f prime equals 0, we have critical numbers. Yay. Good job. Good stuff. Awesome. Okay. So these are pretty good. Reference these a lot. Maybe you don't need to pink sheet them, but definitely learn this process, okay? So basically, you just basically make a sign chart for f of x. All right, that'll give you for f prime of x. That'll basically give you all the critical points and then all the intervals where f prime is either negative or positive. Okay, let's move on to this next one, 5.4. The first, so 5.2 is all about finding critical points, right? It was just about finding critical points, though. It wasn't we did not get down to specifics. We did not get down to like these 3 specifics. We just wanted to find where our critical points were. 5.3 is all about finding intervals where it's increasing or decreasing. All you do is just look at where f prime is positive and negative, okay? This next one then is going to be, okay, let's say we found all of our critical points. So this is basically the topic of this is how do we classify our critical points as either local minima, maxima, or inflection points. Okay. We use the first derivative test. Okay, so basically, you're still, let me boil this down. Basically, what this boils down to is basically you're still making a sign chart for f prime of x, okay? You make the sign chart, okay? And now what you're doing is, so I'll go back to this last problem. You make a sign chart for f prime of x, and now instead of just like finding where f prime equals 0, so these 2 pink points, instead of just finding these 2 pink points, we're going to look at what's going on to the left and to the right, okay? So we know f prime of x equals 0 here, okay? An additional piece of knowledge is we know it changes from positive to negative at this 0. At this one, f prime changes from negative to positive, okay? So the fact that the f prime equals 0 here tells us it's a critical point, and then what kind of sign change is going on at the point tells us what kind of critical point, okay? And right here, this is importante, okay? Let me make this bigger, okay? Here you go. Okay, so if f prime changes from negative to positive, right, then f of c is a relative minimum of f, okay? So negative to positive, it's a relative minimum, okay? So right here, right, so we know this is a critical point because f prime equals 0 at that point. Now we know that it's a relative minimum, right? This is a relative minimum of f. Oh my gosh, sorry guys. Relative minimum of f, right? And why is that? How do we know what kind of critical point it is? Because it goes from because f prime goes from negative to positive at that point. Here, f prime is equal to 0 here, so we know it's a critical point, right? And now we know that there's going to be a relative maximum here. Why is that? Well, we know we have the additional knowledge that f prime of x changes from positive to negative specifically right there, okay? All right. All right. And then this third option, these are going to be in our I'm going to highlight it in a different color. These are going to be if f prime does not change sign. So that would be like if you have, like, let's say you have the graph of f prime of x, okay? And if f prime of x had a 0, let's say like if f prime of x had a 0 where it doesn't go through the axis but just bounces off, right? Then that's a critical point where f prime of x equals 0, right? It equals 0 here, but it never changes sign. It never goes from negative to positive. It just goes negative, hits 0, then becomes negative again. Okay, so it doesn't change sign. If that happens, we call this an inflection point. So an inflection point of f. It looks like, well, in multivariable calculus, they're called saddle points. They don't look like saddles in regular and single variable calculus, and that's because you can't have a saddle in one dimension, or 2 dimensions. But yeah, it looks like, here we go. Here's a relative minimum. This is what a relative minimum looks like. Here's where, like, it's just a little valley, little mountain valley. Relative minimum right here, okay? Here are, these bottom 2 are inflection points. Okay, these bottom 2 are inflection points, right? F prime equals 0 here, right? The slope of this tangent line here would be 0, but it's neither a local minimum nor a local maximum, okay? Here we go. Let's do these examples. Easy peasy. Example 1, find the points that are relative extreme of the function on the interval 0, comma 2 pi. So what does this mean, relative extrema? What does it mean for a point to be a relative extremum? It means that, let me do this one example, then I'll stop. It means that f prime of x equals 0 or is not defined. All right? And that f prime of x changes sign at that point, okay? Right, so we have the additional, right, so a relative extremum is a critical point, so either f of prime of x equals 0 there, or it's not, or it doesn't exist, okay? That's one option. That's one option, okay? Right? And additionally, right, if it doesn't change sign, then we're going to have an inflection point, okay? So a relative extremum is either going to be a relative maximum, where f prime actually changes sign from positive to negative, or relative minimum, where f prime changes sign from negative to positive, okay? So if f prime equals 0 or isn't defined but doesn't change sign, like at an inflection point, then we're not going to have a relative extremum, okay? So these are our two requirements to have a relative extremum. So let's find f prime of x, 1/2, what's the derivative of sine? Cosine minus cosine. Sweet. So that's f prime, okay? And what we need to do is we need to set it equal to 0 or undefined, okay? So that's going to be cosine x equals 1/2. Okay. So we want all the x's between 0 and 2 pi. What is that, exclusive? Yeah, exclusive, such that cosine x equals 1/2. All right, so let's draw our triangle. Let's draw our triangle. All right, this is pre-cal review, but I know you guys probably forget all this, so. Let's draw a little pi over 3. Let's draw a little triangle. Okay, here we go. Okay, so pi over 3 is 1. And again, draw your quadrants, sexy tiger cat, okay? So cosine is going to be equal to positive 1/2 in these two quadrants, quadrant 1 and quadrant 4, okay? All right, so cosine of pi over 3 equals 1/2 based on our drawing. And then the equivalent angle in the fourth quadrant, which is 2 pi minus pi over 3. So what's that? 6 pi over 3 minus pi, so 5 pi over 3. Cosine 5 pi over 3 is going to equal 1/2, okay? You should remember that from pre-cal, but except you probably don't, which stinks. So yeah. So we know in the first quadrant, cosine's positive. Okay, drawing our special triangle here, the cosine, we can see that from our picture. Cosine, SOHCAHTOA, adjacent over hypotenuse. Cosine pi over 3 equals 1/2. And then basically the fourth quadrant, cosine's going to be negative in these two quadrants, so it can't be equal to 1/2 in these two quadrants. In this fourth quadrant, cosine's going to be positive again. Okay, so the fourth quadrant equivalent, the quadrant 4 equivalent of the angle pi over 3, it's going to be right here. This angle is 2 pi minus pi over 3, which is 5 pi over 3. So cosine of 5 pi over 3 is going to be equal to 1/2. So we, yeah, there you go. Yeah, I don't know what else to say. Yeah. So then x equals pi over 3 and 5 pi over 3 are going to be our candidate points. Okay, so okay, this is going to be our two candidate points. All right. And so if we do something to the left of pi over 3, like 0, if we plug in 0 to the derivative function, we get f prime of 0 equals 1/2 minus cosine of 0, which equals 1/2 minus 1, which is less than 0. So it's going to be negative here. Okay, let's plug in something between these two. pi over 3, 5 pi over 3, what can I plug? Let's think. Pi over 2, I can put pi over 2 in there. So f prime of pi over 2 is going to be 1/2 minus cosine pi over 2, which equals 1/2, which is greater than 0. So between here, f prime is going to be positive, so I'm making a sign chart. And then let's plug in 2 pi, okay? F prime of 2 pi. I'm plugging in 2 pi. I got that because I want a value to the right here, so I can fill in the sign chart to the right, in the right region. F prime of 2 pi equals 1/2 minus cosine of 2 pi. Cosine of 2 pi, I believe, is 1, equals 1/2 minus 1, which is negative 1/2. So it's going to be negative again, okay? Good. So I'm going to plot these points in pink. So this is a sign chart I just made for f prime. Okay, this is a sign chart I just made for f prime of x, right? Because f prime equals 0 at these 2 points and changes sign at these 2 points, because of those 2 things, I know that pi over 3 and 5 pi over 3 are going to be relative extrema for this function, okay? All right, I'll stop talking. So we'll do the, we'll definitely try to finish the 5.1, 5.2, and 5.3 skill builders in class, okay, in class on Tuesday. And then 5.4 we'll try to start, okay? So that's my big thing. I think I'm going to have 5.3 due on the Monday after Thanksgiving, but on Tuesday we can take a whole work day, okay? We can hopefully get a lot of it done. I'm hoping to bring my sister in. She'll be able to help you guys, so we'll have double the help. 12 students, 2 instructors. All right, you guys take care.